Welcome to this explainer. If you've ever wondered how engineers actually figure out what's going on inside the incredibly hostile radioactive environment of a nuclear reactor core, well, you're in exactly the right place. Today, we're going to use a super familiar metaphor, a car dashboard, to totally demystify the complex math behind nuclear reactor physics. By the end of this, you'll understand exactly how the experts track the absolute lifeblood of a power plant. Before we tackle the heavy physics, here's our quick roadmap for the explainer. We'll start with our dashboard metaphor, figure out how to calculate reactor power, define fuel burnup, measure our energy mileage, and finally, look at how operators actually manage the core and refuel the whole system. Let's get into it. Section 1. The nuclear dashboard. Monitoring the core. So we have a pretty fundamental problem in nuclear engineering. You can't just pop the hood and look inside an active nuclear core to check a physical fuel gauge. The environment is intensely radioactive and utterly inaccessible while it's operating. So how do operators actually know what fuel is left to burn? To solve this, scientists have to calculate it mathematically, relying on a really clever system of metrics. Honestly, it helps to think of it exactly like your car's dashboard. Reactor power, that acts as our speedometer. It tells us our current rate of energy production right at this exact moment. On the flip side, fuel burnup is our odometer. It tracks the total cumulative energy we've managed to squeeze out of that fuel over its entire lifespan inside the core. Section 2. Calculating reactor power. Checking the speedometer. Okay, the actual textbook equation for calculating total reactor power might look a bit intimidating at first glance, especially with the integral and the Greek letters, but it's actually incredibly elegant. Basically, this formula represents the fission reaction rate per unit volume per second. Let's break this down logically. It's not as scary as it seems. E sub F is simply the energy released by a single fission. Sigma sub F is the macroscopic fission cross-section, which actually is really just a fancy engineering term for the probability that a fission will even happen. Phi is the neutron flux, meaning the sheer volume of neutrons just flying around in there. So the crucial takeaway here is that this intimidating calculus equation is literally just a way to multiply the energy of each fission by the likelihood of fissions happening and the total number of neutrons present. Then it uses that integral to sum it all up across the entire volume of the reactor core. Just to give you a sense of scale for that first variable, E sub F, a single microscopic atomic fission event releases a massive 200 mega electron volts, or MeV, of energy. It's absolutely astounding. When you multiply that 200 MeV by the literal trillions of reactions happening in the neutron flux across the whole core, well, that's how you generate the massive thermal wattage that has the power to light up entire cities. All right, section 3, defining fuel burnup. Reading the odometer. Our source material defines our mileage, or fuel burnup, in a very specific way. It's the heat energy produced per unit mass of the heavy metal fuel that was initially loaded into the core. Notice a really key detail there. It's based on what you start with, not just the tiny fraction of mass that physically gets consumed or converted into energy. Now, there's a crucial caveat here in the engineering world. Nuclear fuel isn't always pure metal, right? It's often formed into chemical compounds like oxides, carbides, or nitrides, just to make it more stable. But when we calculate burnup, we strictly use the mass of the pure metallic heavy metal fuel. We completely ignore the weight of any oxygen or carbon atoms it might be mixed with. We just want a pure measure of heavy metal efficiency. Furthermore, we measure the raw heat energy produced by these fissions. We do not measure the final electricity the plant generates. See, a power plant loses a lot of energy when it converts steam heat into grid electricity. So measuring thermal output gives us the true, unadulterated metric of what the fuel itself actually accomplished inside the reactor. Section 4. Measuring energy mileage. Reading those odometer units. So how do we calculate this in the real world? Well, engineers use two primary, distinct ways to measure burnup. The first formula gives us megawatt days per metric ton, basically calculating the heat power over time divided by the fuel mass. The second formula takes a much more microscopic approach, measuring the atom percentage of the fuel that is successfully fissioned. And there's a massive difference in fuel efficiency targets across different reactor technologies. For instance, a standard thermal reactor, it might target a burnup of a few thousand megawatt days per ton, but a commercial fast reactor, its target is an incredible 100,000 megawatt days per ton before the fuel ever needs discharging. To put that into perspective,
If we translate that huge target of 100,000 megawatt days per ton into our other unit of measurement, it essentially corresponds to fissioning about 10 atom% of the total available fuel. Think about that for a second. That means even in a highly advanced fast reactor, an astounding 90% of the heavy metal atoms haven't even fissioned by the time the fuel cycle ends.
Section 5. Core Management and Refueling. Refueling the reactor. Over time, the number of usable fuel nuclides in the core naturally decreases. This depletion happens primarily due to the active fissions that generate our power, of course. But it also happens because of non-fission neutron capture, which is where an atom absorbs a neutron but doesn't actually split, as well as just natural radioactivity. Together, these processes slowly but surely drain our nuclear gas tank. But here's a totally fascinating logistical challenge. Burnup is space-dependent. Because the highest fission rates happen right at the very center of a homogeneous core, fuel burnup isn't uniform at all. The middle burns out way faster than the edges. It's exactly like having a car, where the center cylinders of the engine wear out 10 times faster than the outer ones.
And this leads us to a crucial operational reality. You run the reactor at a constant power level until, after a set period, say 6 months, depletion takes the core to subcriticality. Basically, it can no longer sustain the chain reaction. To fix this, operators have to run complex maintenance. Because of that uneven spatial burnup we just talked about, they don't just throw everything away. No, they periodically shuffle the fuel locations, moving less burned fuel from the edges into the center. Then they selectively discharge the fully spent fuel and recharge with fresh assemblies just to keep the engine running safely.
Ultimately, understanding this dashboard of power and burnup is exactly what allows us to safely harness the atom. But considering the massive leap in efficiency we see between older thermal reactors and fast reactors hitting that 100,000 megawatt day milestone, it leaves us with a really provocative question. If we are still only burning 10% of the atoms in a fast reactor, just how far can we push nuclear engineering in the future? Could we eventually design a system that burns 50%? Or even 100% of its fuel? Now that is a frontier of physics absolutely worth watching. Thanks for joining me on this explainer.